Welcome to This Explainer. Today, we're demystifying one of the most profound and honestly terrifying achievements in human history, the sheer immense power of nuclear weapons. We're going to trace the science from the invisible world of subatomic particles right up to the horrifying reality of citywide destruction. Let's get right into it.
You've probably heard this before. When J. Robert Oppenheimer, the scientific director of the Manhattan Project, witnessed the first successful atomic test back on July 16, 1945, in the New Mexico desert, he famously recalled a line from Hindu scripture, "Now I am become death, the destroyer of worlds." That single, chilling quote, it perfectly captures the terrifying reality of what their breakthrough actually unleashed upon the Earth.
Now, the underlying concept here almost sounds like magic until you really break down the physics. I mean, how exactly does losing a microscopic fraction of mass translate into such catastrophic, city-leveling destruction? How does that actually happen?
To figure this out, we're going to follow a logical path today. First, splitting the atom. Second, designing the bomb. Third, the anatomy of an explosion. And fourth, the extent of destruction.
All right, part one, splitting the atom. To understand nuclear energy, we really have to contrast it with what we're used to, which are chemical reactions. You know, when something burns or explodes chemically, like TNT, atoms are simply sharing or transferring electrons to form new bonds. The law of conservation of mass holds perfectly true. No mass is lost whatsoever. But nuclear reactions, they are an entirely different beast. They fundamentally alter the nucleus of the atom itself, and when that happens, the law of conservation of mass is actually broken. A tiny, tiny bit of mass is permanently lost and converted directly into pure, unadulterated energy. So, how much energy are we talking about here? Well, using Einstein's famous E equals mc squared equation, a tiny loss of just one single atomic mass unit converts into a staggering 931 mega-electron volts. Let's put that into perspective with some real-world numbers. If a nuclear reaction loses just 0.0001 grams of mass, it releases 9 billion joules of energy. It's literally an astronomical return on a microscopic loss. Think of the nucleus of a heavy, unstable atom like uranium-235, kind of like a giant water balloon. When it's bombarded by a slow-moving neutron, it absorbs it, becomes incredibly unstable, and starts to wobble. Just like a squeezed water balloon, it deforms until those repelling forces inside become way too great, and bam, it dramatically splits apart into two lighter atoms, like barium and krypton. And in that process, it releases a massive amount of energy, plus a few more stray neutrons. Those stray neutrons then fly off and hit other uranium atoms, creating a self-sustaining, completely runaway chain reaction. Okay, moving on to part two, designing the bomb. Now, what's really fascinating is how scientists took that abstract subatomic chain reaction and actually engineered physical devices to trigger and weaponize it. The simplest design for this is the gun-type fission weapon. This is the exact design used for the little boy bomb dropped on Hiroshima. Imagine inside the bomb casing, an explosive propellant is used to literally fire a hollow, subcritical projectile of highly enriched uranium down a smooth barrel. It shoots down and slams right onto a cylindrical uranium spike at the other end. The exact moment they violently connect, they form what's called a supercritical mass. The neutrons begin to multiply instantly and the bomb detonates. Now, it's actually wildly inefficient, right? Because it consumes only a tiny fraction of its fuel before blowing itself entirely apart. But mechanically speaking, it's a very simple design. However, researchers quickly realized they had a problem. Another fuel, plutonium, was just way too unstable for a gun barrel design. It would basically pre-detonate and just fizzle out. So they had to design a much more complex implosion-type device. This was the Fat Man bomb. Here, they took a subcritical sphere of plutonium and surrounded it with this spherical arrangement of specially fabricated chemical explosives, which they called lenses. The trick here is that these explosives must detonate at perfectly precise microseconds. Why? To create a uniform, inwardly directed shockwave that physically crushes the plutonium core. It crushes it until its density drastically increases, pushing it right into that supercritical state. But you know, modern weapons don't just rely on this raw fission process anymore. To make them vastly more efficient and a lot smaller, designers use a brilliant technique called fusion boosting. Right before that implosion crushes the plutonium pit we just talked about, a 50-50 mixture of deuterium and tritium gas is injected right into the hollow center of the core. As the fission reaction kicks off and temperatures absolutely spike, this gas undergoes thermonuclear fusion. Now, the fusion itself doesn't actually add much explosive yield, but what it does do is flood the core with high-energy, fast-moving neutrons. This exponentially accelerates the fission chain reaction, allowing a whole lot more of that plutonium to split before the bomb inevitably blows itself apart.
Let's take a look at how this builds into the truly terrifying modern arsenals we have today, staged thermonuclear weapons, or hydrogen bombs. In these devices, that boosted fission bomb we were just discussing, it acts merely as a primary trigger. That's it. The massive X-ray radiation from that primary explosion is then channeled to ignite a completely separate secondary fusion stage containing lithium deuterium. This two-stage process unleashes yields that are literally thousands of times more powerful than the weapons used back in World War II. It's just mind-boggling.
Which brings us to part 3, anatomy of an explosion.
With the mechanical engineering clear, let's explore the anatomy of the explosion itself, right as all of this immense energy escapes the bomb casing. When we're talking about a nuclear explosion, the timing is incredibly tight. I mean, the actual fission generations, that multiplying of neutrons and splitting of atoms, they happen in mere fractions of a microsecond. Within a single millisecond, a blinding fireball of X-ray radiation is fully formed. And within just 10 seconds, the fireball reaches its maximum size, and a devastating shockwave has already traveled over 3 miles from ground zero. It happens in the blink of an eye. That vast energy released in that microsecond distributes itself into 4 terrifyingly destructive elements. First, you have the immense blast and shockwave. Second, the intense thermal radiation, or heat. Third, the immediate, highly penetrating nuclear radiation. And finally, number 4, the residual radioactive fallout that poisons the environment long after the explosion is past. Now, the absolutely crucial point when it comes to immediate physical destruction is the blast wave. The shock front actually behaves like a rapidly moving, invisible wall of highly compressed air. As it travels outward from the fireball, it creates this crushing ambient pressure spike over the surrounding landscape, basically pushing structures to their absolute breaking point in an instant. And that leads us to part 4, the extent of destruction. Zooming out from this subatomic physics to the ultimate macro level, we really have to look at the physical toll this extreme heat and pressure takes on the human environment. In the aftermath of the explosion at Hiroshima, the vast debris field reveals a truly haunting reality. The crushing action of the blast wave was so profound that it literally snapped telephone poles off at ground level like dry twigs. It turned the entire city into a vast sea of fragmented, pulverized debris. Glass, wood, masonry, metal, the whole shebang, which tragically in turn sparked unstoppable secondary fires across the ruined landscape. Data gathered from the Nevada test site perfectly illustrates the incredible force of that invisible wall of air we talked about. Take a perfectly rigid, steel-framed industrial building. After being hit by a peak overpressure of just 3.1 pounds per square inch, the entire structure was completely bent, twisted, and demolished. The walls and roof caved in as if swatted by a giant hand. It's just staggering to think about. Yet, interestingly enough, the shape and mass of a structure greatly dictates its survival. While those lighter industrial buildings were completely torn apart, massive earthquake-resistant structures, like a 60-foot circular reinforced concrete stack in Hiroshima, managed to withstand the blast remarkably well, even being just a third of a mile from ground zero. This was largely due to its immense mass and its circular shape, which lacked aerodynamic drag. Basically, it allowed the shock wave to just flow around it rather than catching it flat on. Grounding all of this abstract physics and engineering back into our reality is the Trinity test fireball, captured exactly 0.025 seconds after detonation. I mean, you can literally see the heat vaporizing the test tower and just churning the earth below. It is the exact moment humanity tapped into the fundamental building blocks of the universe, and for sure, forever changed the course of human history. So, I'm going to leave you with this final, provocative thought to consider as we wrap up this explainer. Having engineered the ultimate power to dismantle matter at a microscopic level, how will humanity ensure we never again unleash it on our macroscopic world? Thanks so much for joining us, and keep asking questions.